We will be discussing about the most basic experiments in control. The first one is the simple first order thermometer system, and the second one is that of the thermowell system. So first we have this thermometer. On the other side of the board I will discuss this thermowell system, which is nothing but the first order pseudo system. We will see what that exactly means. So to start it, we just have to understand the setup. We have this heater first, which is equipped with the magnetic stirrer. So you have this oil bar, in which this is the magnetic stirrer. So you have the provision over here, which can be used to adjust the speed of the regulator as well as the heating temperature. So in the thermometer system, your thermometer is directly dipped into this oil pan. So in the simple experiment, you allow this temperature of the oil to reach around 90 to 95 degrees Celsius. So that will take a bit of time. After it reaches 90 to 95 degrees Celsius, this is of course connected to a stand over here, this thermometer. So after it reaches 90 to 95 degrees Celsius, you suddenly take it out. So what do you do by doing so? Is you are exposing it to a step change. For example, before you expose it to the atmosphere, the temperature inside this and that indicated by the thermometer is 90 to 95 degrees Celsius. But when you take it out and expose it to the atmosphere temperature is say around 30 to 35 degrees Celsius. So in a way you are giving a step change of 90 to 95 minus 30 to 35 degrees Celsius. So that will be around 60 degrees or any particular value. So this value A, which is the step change, can be used in our experiments. So for a simple thermometer system, the transfer equation, which in Laplace domain in control it is denoted by Ts, which is nothing but y of s upon x of s. Y of s is nothing but the response, and this is the input. So if you derive it, that goes like 1 upon tau s plus 1, which is where tau is nothing but the time required to reach 63.2% of the response. So that also we will see what it is. So x of s in our case is the step change, which is a by s. So when you put a by s over here, y of s, which is response in the Laplace domain, will be, if you just take it out, it will become a upon s tau s plus 1. So after integrating, we have to just integrate it to convert this into the time domain. So after you do so, you get this type of a response. Y of t is equal to a into 1 minus e raised to t by tau, where tau is the time constant, which is the only unknown in this equation. So in the simple experiment, what you will do after exposing it to the atmosphere, you will take readings for every 2 or 3 degrees drop in temperature. So for example, you just have to prepare a table like this. For example, time t equal to 0, you have the temperature that is indicated as 95 degrees Celsius. So let's find out the time, for example, which is required to reach 92 degrees Celsius. So corresponding time for 92, 89, 86, 83, in a similar manner till you reach another steady state, say around 35 degrees Celsius. So you have to correspondingly note down the time for each temperature. After you do it, you will get a plot. That will be the temperature y of t versus time. So it will be the typical first order system. This is the typical first order system equation. So experimentally you may get a plot like this. What you have to do is you have to basically verify whether this system follows the first order or not. So this y of t, which I am calling it as a small y of t, is nothing but the change. So this is not the temperature. This is a change. The change which you are giving to the system after giving a step input. So the final temperature, which I am calling it capital Y of T, is nothing but your P naught, which is say 90 to 95, the temperature from where you have started taking the readings or started the experiment, minus this small y of T. So you have to just find out in this equation the unknown tau. So what is tau? Tau is nothing but the time required to reach 63.2% of the total response. So for example, when your temperature is 95 and finally you are reaching a temperature of 35 degrees Celsius. So 35 degrees Celsius, the total change which you are giving is 60 degrees. This is the total change. So 63.2% of this total change, which will be around 39 degrees Celsius. I am just telling you approximately. So 95 minus 39 will be the temperature, which is say 56 degrees Celsius. So you have to basically find out the time at which the temperature becomes 56, which you can do even by extrapolation or by just taking the approximate. For example, if you go like this, you will get at 56 degrees Celsius what is the time. So that time will be nothing but the time constant of the system. Another unknown in this is A, which is the step change. This step change is nothing but T initial, which is 95 from where you have started the experiment, minus T atmosphere, that is the temperature of the atmosphere, that's what the temperature you have exposed the system. So I think after doing so, you will get a plot somewhere like this. I am just drawing an approximate plot. So this will be your experimental response and this will be your theoretical response. So basically you just have to see whether these two responses match properly or not. There might be a few sources of error. One is that when you take the system out, you have to wipe the layer of oil which is surrounding the bulb, because that may provide the additional resistance as well. So the possible reasons for deviation may be many, but you have to just see how much close your system behaves to the first order system. So this is about the thermometer experiment. The Thermocouple experiment is also to be performed in a similar manner. The only change which you have to do is in the system. So in the system you have this oil well, and in this you have a test tube in which your thermometer is attached. So in this test tube it is filled with water and this is filled with oil. So similar way you have to perform the experiment, same as this one, only you have to understand that here you have only one resistance, the resistance offered by the fluid surrounding the bulb. Here you have two resistances, one that of the bulb, so these are the resistances, one that is of the thermometer bulb, and second is that of the fluid surrounding thermometer. So this is the Thermocouple system, this which I am encircling right now, this is the Thermocouple system. The basic advantage of this Thermocouple system is that if you want to keep a section of fluid in the industry which is away from all the surrounding temperature, for example if you want to maintain a particular temperature in some areas, then you can use this type of a system. But it may be disadvantageous as well, because in some cases if your entire system is getting affected by some changes, it may not reflect over here. So you have to use this system a little bit wisely. So as I said that there are two resistances in the system and you have to perform the experiment in the same way. So as I said that let's allow the system to reach 90 to 95 degrees as the same way using the heater and the stirrer system, magnetic stirrer system. And after you do so, you have to lift this entire system up and expose it to the atmosphere. So you have this Thermocouple system and you have this thermometer inside that is exposed to the atmosphere at time t equal to 0. In the similar manner, you will see you have to take the readings of time versus temperature. The only difference being that you have two resistances. So the difference between these two experiments is that you will observe that this temperature starts dropping very rapidly initially. Whereas compared to this one, this temperature will take little bit of time because of the additional resistance. So you will also plot the same equation and the same system. You will plot the same thing. You have this y of t, which is the response, the capital Y, versus the time. So you have this, you will get some plot like this. So this is the experimental observation. The area of concern is this part, where the drop in this part may not be as sharp as drop in this part because of the resistance. So how we will match it with the available models? The first part is the simple first order model. As I said, that it is a pseudo first order system. What do you mean by pseudo first order system? So when you do the calculations for the thermometer part, you will realize the time constant for the thermometer system is quite low, maybe around 1 minute or 1.5 minutes, maybe 90 to 100 seconds. But when you do it for the thermocouple system, you will realize this time constant for the overall system. If you adopt the same methodology as I said to calculate the time constant, as I said in case of thermometer, you will realize that the time T2, that is the time constant of the thermocouple, will be around 900 to 1000 seconds. That is, I am just giving you the approximation. So in a way, tau1, that is the time constant for the thermometer, is very much lesser as compared to tau2. So because of this condition, even though there are two resistances, the resistance offered by this bulb becomes negligible. So you have only the resistance offered by the fluid surrounding the thermocouple, and that's why it can be approximated as the pseudo first order system. So this is just what we presume. So the second part is that we also have to verify whether it really follows the first order system or not. And another part is that we have to also see whether how good the second order equation holds true. So the first part is very simple. We have to perform the calculations in the same manner as I explained in case of the thermometer. The equation for the change, that is small y of t, is a into 1 minus e t by tau. So in this case, a is nothing but the step change, that is the same as I said in case of thermometer, and the tau is the time constant of the overall system. So you will get a particular plot, and you will get, say for example, something like this for the first order system. This is just what I am presuming. You may get a different result as well. So for the second order system, the equation becomes a little bit complicated. That is given very nicely in Bucknell actually. So since there are two resistances, you can approximate it as a little bit of complicated equation that we have. It is the equation given in Bucknell, goes something like this: 1 minus e of t by tau epsilon t by tau into cos of hyperbolic epsilon square minus 1 into t by tau 1 plus epsilon upon epsilon square minus 1 under root. I will be coming to this, what is epsilon naught, sine hyperbolic square root of epsilon square minus 1 t by tau. So you just have to verify whether this equation holds true or not. So what is this epsilon? So you will realize that this is epsilon is nothing but the damping coefficient. Epsilon is the damping coefficient. So if you read your theory properly, you will realize that if epsilon is equal to 1, this becomes a critically damped system. So for a critically damped system, the example is that of the simple two-tank system, interacting or non-interacting. You will get that your value of epsilon will be very much close to 1. This is simply because of the fact that the time constants tau1 and tau2 are very much close for the two-tank system. Epsilon greater than 1 is the case of the overdamped system. This is what we are basically dealing with, the thermocouple system. This is the case when the two resistances are far apart. The resistance offered by the thermometer is very much negligible as compared by the resistance offered by the fluid surrounding the thermometer. So this is what we are dealing with, and xi less than 1 is the case for the under damped system, and for that the examples are there in plenty. Even in the laboratory you can perform it and verify what is the value of psi. So for our system, the system equation looks like this. The basic transfer function, which I denoted as T of S, which is the response upon the input, is nothing but K upon tau square S square plus 2 xi tau S plus 1. Okay, so if you compare it with our system, you will realize that 2 xi tau is nothing but tau 1 plus tau 2. So xi is nothing but tau 1 plus tau 2 upon 2 tau. And what is tau? Tau is nothing but, tau square is nothing but tau 1 into tau. So you have this because you are tau square S square, which you, if you derive the equation for the thermowell, you will realize that tau square, which is the coefficient of this S square, will be nothing but tau 1 into tau 2. So you just have to, since we know tau 1 is the time constant of the thermometer, tau 2 is the time constant of the thermowell system. So basically you know the tau, the value of tau, because you have calculated it experimentally using the 63.2% concept, as similarly in case of the thermometer. So you know this value of tau, so you know the value of tau 1, so you can calculate tau 2. Tau 2, once you calculate tau 2, you can get the value of xi as well, because tau 1 is known, tau 2 is known, and tau is also known. So you will realize that this value of xi will be greater than 1. So that verifies that this is the overdamped system. So that's all. Then we can just proceed and see how the experiments are actually performed.